All right, let's talk about free body diagrams then. What a free body diagram is a diagram of your problem where you've labeled all of the forces and they're all pointing in generally the right direction, okay? In a free body diagram, it's really important that all forces get an arrow and there should be no arrows on a free body diagram that aren't forces, okay? So don't put any velocity vectors on a free body diagram. Don't put any acceleration vectors, nothing like that. You're not even going to put a net force on a free body diagram. You're just going to put all of the individual types of forces, okay, that are involved in this specific problem. So there's 4 different types of forces you're going to want to look for to put on your free body diagrams for right now. Later we'll get to friction and other forces that are like spring forces and things like that. But for now, just tension, weight, applied forces, and normal forces. Okay, tension, you know about tension, right? Tension is the thing that happens when your professor is going over time in his lecture and everybody's upset about that and wondering when he's going to stop. That's one kind of tension. There's another kind of tension that goes on your free body diagrams, though, and that's the force that's carried by a string, right? So tension in strings brings about a force. So tension forces, it's important to remember that the magnitude of the tension force is the same everywhere along a string, okay? Tension forces pull, they never push, and but you can use, say, things like pulleys to redirect the direction of forces. So here I have an example, right? I have one box here that's connected by a string over a pulley here. Okay, this is a little pulley there, and it's connected to another box there. Now, the magnitude of the tension force is the same everywhere along the string, which means that, so if I take red to be the color of the forces that I'm going to draw on my free body diagram, so there's going to be a tension pulling up there. Okay, I'll label that T, right? There's also going to be a force exerted on this box there, right? That's going to have the same magnitude, T, right? But obviously it's pulling in a different direction there, right? And so long as the pulley is massless, it's an ideal pulley, then those two tension forces are going to be exactly the same. Okay, so this is important. Massless strings and ideal pulleys are the things that serve to redirect these forces, and they show up a lot in our problems. Okay, number 2, weight. Okay, so this is, when I say weight, I do not mean mass. Things that are massive and are in the presence of some gravitational body have weight, okay? Weight is mass times gravity, for the most part. You can watch Walter Lewin's lectures to see that it's a little bit more complicated than that. Like when you're in an elevator, you could argue that weight is different, right? The thing that a scale would read while you're accelerating upwards would be greater than actually mass times gravity, but that's besides the point. So for the most part, you're going to have weight that's equal to, right, or the force of gravity that's equal to the mass of an object times little g. Okay, little g is the acceleration due to gravity. So for something that so we know that force is mass times acceleration, right? Even if something is sitting, say, resting on a table, or if I take this book here, right, and I just set it there on my hand, okay, the book has a gravitational force pulling down on it that's equal to its mass times little g. Even though it's not accelerating, it still has that force there. It's just that the force of my hand is pushing the thing up so that the net force is 0. On my little diagram here with the 2 boxes, I've already included the tension forces. Now, if I'm going to put the weight on there, right, I would put it down like this. And I would say, since this is mass 1 here, I would call this Fg1, and this is mass 2 here, I would call this Fg2. Okay, so the gravitational force on M1 and on M2. Now note, right, the tension here, the magnitude of the tension force was exactly the same, so I put the same symbol on there. I put T for both of them. Here, they have, in principle, they could have different masses, this M1 and this M2, so I put Fg1 and Fg2 on there and labeled them with a different index to show that they could have different forces on the free body diagram. Okay, so that's weight. We've done tension and weight. Now applied forces. Those are the simplest ones. This is just like, say that this guy comes in and he pushes on this mass there. He introduces some applied force. Right, this way here. And so we'll call that FA, F applied. An applied force is just some force that gets introduced and really doesn't get explained very much. So something like a push. And finally, the normal force. Now the normal force, the word normal, it just means perpendicular. Normal forces are exerted perpendicular to a surface. Okay, so here my box is sitting on the ground, M1 up here is sitting on the ground, so the normal force would go up. It's exerted by this surface on the box that's resting on the surface. It points up against gravity there. Okay, what about M2? Well, M2 is suspended in the air, so there's no normal force on M2. Something to keep in mind is that, if you have some kind of an inclined plane or something like that, the normal force is not always up straight against gravity. It's always perpendicular to some surface. Okay. All right, so I have labeled all of the forces here that are involved on this particular example problem. They're all there in red. So this is the free body diagram. Now, you're going to get problems on your homework and on exams and stuff that look like this, and then they ask you to solve for certain things. But the first part of those problems usually are just going to have something like, part A, tell me what is the free body diagram. And you have to draw it exactly like this. Okay, let's do some other examples. So, where I'm just going to get the free body diagram. So here I have Tarzan swinging on a vine through the canopy, through the forest. What forces are involved here? Pause this video and draw them yourself. Okay, now I will do it. So this is Tarzan, he's swinging through the forest, right? He has weight, right? There is a gravitational force pulling down on him. There is also a tension force that acts along the string, pulling him up in this direction here. So there's an Ft, a tension force, and Fg, a gravitational force pulling straight down on him. And one other thing that I would recognize, or that I would recommend that you do, is get rid of this thing, okay? Because all forces get an arrow, and no arrows that aren't forces, right? So I had that little arrow on there to show you which direction he was swinging in, but that's not a force, so I don't want to include that on my free body diagram. Okay, just want to make sure that this is clear, that this is F sub G, right? Gravitational force, or the weight. Okay, now what about this one here? If I have a person pushing here against this box, what would the free body diagram look like? Pause the video, try it out yourself. Okay, so there's an applied force that's pushing on the box in this direction, force applied, and there's weight, the box has weight, so there's a gravitational force pushing down. And finally, since the box is resting on a surface, that surface is exerting a force on it, so there's a normal force pushing up. That's normal. Okay, I'm taking this to be a frictionless surface since we haven't talked about friction. Okay, next example problem is 27 from chapter 4 in your textbook. It says a box weighing 77 newtons rests on a table. A rope tied to the box runs vertically upward over a pulley, and a weight is hung from the other end. Determine the force that the table exerts on the box if the weight hanging on the other side of the pulley weighs 30 newtons, 60 newtons, and 90 newtons. So I'm going to emphasize problem-solving techniques here, so I'm going to go through this problem pretty slowly, and I hope that this will show you how to go about solving these free body diagram type problems. Just note that some of the first steps are really common to all of these problems, things like read the problem twice, underline or just take note of, write down the things that are given to you, set up a good coordinate system, do your free body diagram, and then I'll talk and emphasize problem solving in this part. So, first I read the problem, then I read it again. I like to underline helpful information and circle given quantities. Then I drew my free body diagram. Okay, now I have MB for the mass of the box and MW for the mass of the weight over there. And you can see, right, I've labeled all the forces. So each one has a force from gravity pulling down, and each one has a tension force pulling up. Right, there's a tension force there, and there's a tension force there. And there's also this normal force here on the box, which is resting on the surface. No normal force on the weight because it's not resting on a surface, right? There's just tension and gravity, otherwise known as weight. Now, you're supposed to write down the given quantities. Okay, I know we were given the force of gravity, right? We were given the weight for both the box and for the weight, right? The force of gravity on the box was 77 newtons, and then the force of gravity on the weight was different, right? Part A was 30 newtons, part B was 60 newtons, part C had it at 90 newtons. Okay, and we were asked then to find the normal force, right? The normal force on the box, the force that the table exerts on the box. So I followed all of those steps. Now I want to explain what my next series of steps are going to be. There's a lot of steps to these free body diagram type problems. Okay, the first one, this is how I like to do it in this order. I like to write down F net equals ma for each object, summing over each of the individual forces first, okay, in their vector forms. So this should actually have a vector form here, because that sum will be true regardless of which coordinate system I pick. So I like to write this down first. After I write down my F net equals ma equation, I like to write down and pick a coordinate system. Okay, now notice this little asterisk here means that these steps should be performed for each object. You can pick a different coordinate system for each object, and you'll see when I solve the problem why I'm making such a big deal about this, because it actually does make a difference for this exact problem. You want to pick a coordinate system that can have this box moving up correspond with this weight moving down, right? That's because you use your physical intuition, you looked at this and thought about it, that should make sense to you why that would be helpful. And that comes in at the level of your coordinate system. Then step 3, I like to take F net in the x component after I've chosen my coordinate system. I like to take F net equals ma from its vector form into its individual components, into its x and y components. So notice here, this is also for each object. So I have 2 objects. In this case, I only have one dimension. There's only one coordinate. Everything's either moving up or down. But in other problems, you might have x and y components that are important. If you have multiple, say you have 2 objects and you have 2 coordinates, you're going to end up then with 4 equations here. So make sure that you have them all. Okay, the next thing I like to do, step 4, count the number of knowns and the number of unknown quantities. Okay, make sure you have enough information before you start messing with equations, because people do this on tests all the time. They sit there and they do tons of math and they never realize that they got tripped up and right up here at the top because they never got enough equations in the first place. So there's no point in sitting there and doing a ton of algebra if you don't have the same number of unknowns as you have equations. So this is really important. Step 5, solve the equations and do that in terms of symbols, okay? Don't plug in numbers until the very end. It'll make your life a lot easier. So solve the equations for whatever you're supposed to find. Step six, plug in the numbers and make sure to keep your units along with the numbers so that you'll know the units of the final quantity. Most of the time it's going to be in terms of SI units anyway, but keeping your units is a nice check to make sure that you didn't drop some factor or something. If at the end you're supposed to find a force and it comes out in units of meters per second squared, then you must have at some point forgotten a mass, dropped a mass. And so if you keep your units along in there while you plug in numbers, you will have that nice check on your answer. Okay, and then finally, step 7, check your answer. And there's a lot of different things that you can do to check your answer. You don't have to use Google. That's not what I mean by checking your answer. Okay, what I mean is use your intuition, use rough estimates, and use certain limiting cases. Okay, here's what I mean by this. Intuition. Does it make sense? Does it make sense? So if I came up in this problem with an answer that said, say that this box is going to accelerate, have a negative acceleration, and I picked the coordinate y going up, so negative acceleration means that this box is going to plunge through the surface here. Okay, that doesn't make sense, right? Your intuition tells you that the box is not going to plunge through the floor, so this would be this would tell you that you've done something wrong and you need to go back and rethink something, right? Likely a coordinate problem. Next thing you can do to check your answer, rough estimates. Okay, so if you're asked in some problem, say, to find the speed that a car is moving from one city to the next, and you find that the speed is like half the speed of light or something, well, you probably did something wrong. If you're asked to find the time that it takes to drive from New York to San Francisco, and it takes 4 seconds, you probably did something wrong, right? You can use your own rough estimates from just thinking about it. Final thing, limiting cases can be helpful. So I'll give you examples of these later, but say there's an example. So here's a good example of a limiting case. So in this problem here, right, we have a box resting there and we have a weight over on the other side. A nice limiting case would be if you take their weights to be equal, okay? You can find answers for, say, the acceleration of the system in terms of their two masses, and then you can just say, well, a good way to check my answer would be, does this make sense if I say that they both have the same mass? If you have some factor of, say, mb minus mw in the denominator of your acceleration, then the limiting case that I've chosen here, right, where the two things are equal, well, that would mean that if you have an mb minus mw in the denominator, that would go up to infinity, right? The acceleration would. So that's an example of a limiting case that you can use as a check on your answer. You know that that can't be right then, and you have to go back and rethink some things. So checking your answer can be really, really helpful for you. And just a few other, just to drive this home one last time, make sure you do an F net equals MA for each object. Make sure you set up your coordinate system for each object, and make sure that you apply that consistently. And number 3 there, make sure that you break these things into their individual components and do that for each object. And finally, before you start going into solving your equations and where you're going to spend some time sitting there and doing algebra, make sure you count the number of knowns and the number of unknowns, and make sure that you have enough equations, right? You need, if you're going to solve for 3 unknown quantities, you better have 3 equations. Okay. All right. So we're back. I'm going to solve the problem now. Just had to erase the board because we're kind of limited for board space down here in the physics basement. But I have it up on the screen for you. I'm going to solve the problem going through these steps. All right. Step 1 was to set up an F net equals MA equation for each of the individual objects. So I have F net on B. That's equal to, right, just looking at the free body diagram, I have a force of gravity, I have a normal force and a tension force. So Fn plus T plus Fg. Note that this is true independent of whatever the coordinate system is. Doesn't matter what the coordinate system is, that's still true in its vector form there. Now, F net on W is just, there's a tension force and a force of gravity, right? There, that's step one. Step two, pick a coordinate system for each object. Okay, this one is kind of tricky for this particular problem. So, if you look over here, you'll note that I have chosen for object B a coordinate system where plus y is pointing up. Okay, y is up for mass B. For mass W, plus y is pointing down. Now, why did I choose them to be pointing in different directions? The reason is because I'm setting things up based on my intuition. I know these two objects are tethered together. Okay? That means they're going to have the same acceleration. If this one, if MB accelerates up, MW is going to accelerate down. Okay, the magnitude of that acceleration is going to be exactly the same regardless of what the coordinate system is. Whatever coordinate system I pick will not affect that. However, if I choose my coordinate system nicely, where plus y is going up here and plus y is going down over here, then they'll have the same direction in addition to the same sign. So that's really nice, because what I'm going to do when I set up these, go on to the next, okay, so I'll continue to explain that as I go into the next step. So in step 3, I'm going to pick the individual components out, right? Thankfully, this is a one-dimensional problem, right? There's no x forces involved here, so I can just set these things F net y in terms of, right, this will be equal to mass B times A, and this will be equal to mass W times A. Right, so there's only, the acceleration only has one component. Now, you'll note here, if I would have chosen this coordinate system differently so that y was, say, going up for both cases, I would have had to put a minus A in here in order to make this consistent, because I would have had to have one going up correspond with the other one going down. So this is one thing that that you learn from doing a lot of these problems over and over again. But another one of the things that's one of the reasons why I gave you this long list that includes number 7, right? Number 7 is right there on the screen, right? It says check your answer. Well, if you would have done this and flipped the axes around the other way and solved the whole thing without putting the minus A here in the end, what you would have is something that, upon checking your answer, by setting the two masses equal, right, that limiting case check that we talked about, you would see that the answer you got doesn't make any sense. And then you might think, maybe I need to pick a different coordinate system, or maybe I need to be more careful with my signs when I put these things in. Okay, something to keep in mind. So I have F net in B is equal to MA, and I can put that in terms of the individual forces, and now I need to be careful to make sure that the signs match up, right? So Fn is pointing up, so it's positive. T is pointing up, so it's positive. And the force of gravity on B is pointing down, so that one is negative, minus FB. Okay, for the mass of the weight, it's equal to, right, there's a tension force that in this case is pointing in the negative y direction, right, minus the tension force, plus then the gravitational force on W is pointing in its positive y direction. All right, so that's step 4. And now I can, sorry, that's step 3, and now I can go on to step 4. Let's count the number of equations I have and the number of unknowns. So I have 1, 2 equations. I'll label them 1 and 2. And I have, well, let's see. This is a known. This is known, right? The acceleration, that's unknown, right? The normal force here, that's unknown. That's what we're asked to find. And the tension force there, that is also unknown. So we have two equations and we have three unknowns. Okay, does that mean that we're sunk, that we can't solve this problem? Of course not. Okay. Whenever you find yourself in this situation, I have two equations and I have three unknowns, that means you need to think. You need to think a little bit more. So let's use our intuition and let's think about this problem a little bit more. Okay. I'm given FGW for part A, B, and C with three different values. Okay. I know something about this system just from my own physical intuition. I know that this weight here, if this one is larger than that one, if this object, the weight here is more massive than the box, then the whole system is going to, this thing is going to fall and that's going to go up, right? And I know that if the mass of the box is larger than MW, that this thing is just going to rest here on the table. So that's something I know. Okay, well, let's think about this. Part A and part B both have FGW is greater, FGW is less than FGB, right? So for A and B, we have FG for the box is greater than force of gravity for W. Okay, if the weight of the box is larger than the weight of the weight of the counterweight over here, then what is the acceleration of the system going to be? Think about it. That one weighs more than that one. That means that thing is just going to rest there on the surface. And that means that the acceleration is going to be 0. Right? The acceleration is going to be 0. So that gives me a third equation, a really helpful one, right? That gets rid of two of them. So let's just do part A and B first. So in that case, right, both 1 and 2 are equal to 0. So I have 0 equals Fn plus T minus FGB, and I have 0 equals minus T plus FGW. Okay, I can do addition or substitution method, right? Here I have two equations, two unknowns. I can use addition or substitution method to find my answer. I'm asked to find Fn, so what I'm going to do is just take this equation and add it to this equation. Okay, I'm going to use the addition method. So if I do that, adding the left-hand sides are they're both 0, so they add together to be 0. The right-hand side, I get an Fn plus T minus FGB, first equation, plus this minus T plus FGW. Okay, now notice that the T and the minus T cancel each other out. So I get that this is equal to Fn minus FGB plus FGW. And in other words, the normal force is equal to, adding across those other two terms, F, the force of gravity, B, minus the force of gravity, W. Okay, this is exactly what I was asked to find. So let's just plug in the two numbers. So for part A, right, that means Fn would be 77 newtons minus 30 newtons, right? That's 47 newtons. In part B, right, it would be 77 newtons minus 60 newtons, which is 17 newtons. Okay, and so I can box in my answer. I have no room to write down part B, but that's fine because it's really pretty much the same as part A. And now I'll erase the board and we'll do part C. Now, in part C, FGW was 90 newtons, and that meant that this weight over here is heavier than this box here. And so, as I have shown here, now I want you to stop, pause the video for a second, and tell me what is the third equation that I get because I know this. Okay, I'm going to take it that you've done that. Now, I'm going to go through and just talk my way through it. If this thing is heavier than that thing, then the whole system is going to move, right? The weight here is going to fall. The box here is going to lift up. Now, if that box lifts up off of the surface, then that means the normal force is 0, right? The normal force would be 0. So, the normal force for part C is 0. And that is our final answer. Okay, but before I let you go, so that this is the final answer, the problem is done. But before I let you go, I do want to talk a little bit about this case and if we wanted to solve for the acceleration. So, going back to our FNet equations here, in the case of part C, right, where the normal force is 0, then I can solve, then my equations here reduce down to, for mv times A, it's tension minus the force of gravity, and for MWA, it's force of gravity minus tension. And I can do the same addition method. What I end up with is, on the left-hand side of the equation, an mv plus mw times A equals a difference between the two weights, right? It's this weight minus that weight. Now, if I solve this then for the acceleration, I have the difference between these weights divided by the masses. And if I put those then in terms of the masses here, I have mass of the weight minus mass of the box times little g over the sum of the two weights. Okay, so you notice here then I have a sum of weights in the denominator and a difference between the two masses in the numerator. Okay, and you know, I was given the force of gravity on each one of these. I would just have to divide this by 9.8 in order to get, right, the mass here. Okay, so let's just do some sanity checks on this because I do want to get all the way down to number 7. Okay. Number 7, some sanity checks. Well, I already said before, a good sanity check would be, what if MB equals MW? Well, if MB equals MW, and we're in this case here where the normal force is 0, okay, then what's going to happen to this system? It's just going to sit there, right? If that weight and that weight are exactly the same, then this MB is just kind of going to be hovering above the surface, right? The normal force is going to be 0, but the acceleration is also going to be 0. And there's a difference between the two masses there in the numerator, so if they're the same, the acceleration of the system is 0. Okay, so that's a good check. That's a good check. Now, what about other checks? What if MW is really, really large and MB is really small? Okay, that means the acceleration would be really large, right? If MW is way bigger than MB. And that's exactly what I get here, right? The acceleration would be really large if MW was big and MB was small. And in the reverse case, right, then we're no longer in this regime where Fn equals 0, so that would not be a good sanity check, right? That would have been a good sanity check on the for the equations that we had derived under parts B and C.